Hello, welcome back. Good morning. All right, so today we're gonna go through the questions and the first law of thermodynamics. All right, so let's get started. So next up, we're gonna look at how to measure the specific latent heat of a substance. So this is actually in your notes, but let me just very briefly outline the steps that you have to do and what data you have to collect. So the specific latent heat equation is delta Q equals to L delta M. All right. So actually, you know what? Let me just do it like this. So if you were to plot a graph of delta Q against delta M, you would expect to get, hang on, let me just do it like this. Delta Q over M, where M is the current mass of the water. So how is the current mass related to the change in mass? Well, the change in mass is actually the original mass minus the current mass. There. Okay, so if you expand this, you get L m naught minus L m, which means if you were to plot delta Q against M, and then imagine superimposing the equation of a straight line, you'll see that you actually get a negative gradient, right? And it kind of looks like that. So this part here is m naught. Wait, hang on, let me think. With m is 0. Yep, so this is actually L times m naught. There you go. And the gradient is going to be equals to negative L. There. So what you want to do here is you put in some water and then you put it on some weighing balance, right? And then you measure what the initial mass of the water is, m naught. But obviously you want to omit the mass of the beaker. So start by measuring the mass of the beaker without the water. And then you put some water in, and then you measure the mass of the beaker and water, and then you subtract the mass of the beaker plus water with the mass of the beaker to get just the mass of the water. Okay, and then once you're done, you can put in the electric heater, and this is connected again to some circuit which you have, you know what the voltage is, you know what the current is, because you have the ammeter and voltmeter and a variable resistor in the form of a rheostat to make sure that these stay constant so that your power stays constant. Okay, and then P equals IV, so P is Q over T, so Q is equals to IV times T, and then you can take that, and that's going to be your delta Q. Okay, so just put that in here. Right. And then what you're going to do is you're going to heat up the water, wait till it boils. So when it starts boiling, you measure the mass again. Oh, sorry, you should have measured the mass when the water is boiling. So this m naught is the initial mass when water is boiling. Okay, don't measure it before it's boiling because you're trying to find the specific latent heat, which is the energy required to change the state of a substance without a change in temperature. So you have to make sure it boils first. So what you can do is you can put a thermometer here. I forgot to draw a thermometer in the diagram, so you can just draw that in. Thermometer to monitor the temperature. Once it reaches 100 degrees Celsius, you check for the mass, you calculate this, okay, and then you let this water start to boil. And as the water boils, the water vaporizes and the mass would start to decrease. So at specific instances in time, so maybe every 30 seconds, you make another measurement. You check the the mass balance, and then you get your first reading, your second reading, third reading. So these would, you know, form like some points on the graph, and then you plot your line of best fit. And that's how you get this line here. And then from there, you use your gradient to find your specific latent heat. So that's what you want to do. Okay, that's pretty much it. Right. Alternatively, you can also try to find the specific latent heat by finding the y-intercept and then equating that to L times m naught. So that works too. But in any case, you have to plot a line of best fit first. And again, you need some insulation to avoid heat loss to the surroundings because that's going to contribute to random error. So that's pretty much all there is to it. You can review that on your notes over here. I don't think I included the equation though, so you might want to write down the equation, and you want to just draw in the the thermometer. Let's draw the thermometer in there. Okay, there we go. And sometimes in the exam, they would ask you, how do you check if the rate of boiling is constant? So you could say by looking at the rate of bubble formation on the surface of the water. So that's one thing you could say. Okay, anyway, we are done. Next up, we're going to look at the first law of thermodynamics. So the first law of thermodynamics gives you an equation that relates the internal energy of a substance, or specifically the change in internal energy of a substance, with the energy supplied and the work done on the system. Okay, so remember that the internal energy, U, is actually the total kinetic energy of all the particles in the system plus the total potential energy of all the particles in the system. So a change in the internal energy would imply a change in one of these variables as well. It could be a combination of the two, or it could be just one of them. And one thing that you want to note is that for an ideal gas, the particles have zero potential energy because we are ignoring all the forces between particles. That's one of the ideal gas assumptions. So for an ideal gas, a change in the internal energy would be directly proportional to the change in the kinetic energy, which is directly proportional to the change in temperature, because the kinetic energy is equals to 3/2 kBT. Remember that? We did this in the last chapter. Well, 2 chapters ago. So that is something important that you have to know. Right, next up, what is this Q here? So Q is the energy supplied to the system. For example, if you were to heat the system up or introduce some energy into the system, then this would be positive. If you take some energy away, this would be negative. And this term here, work done on the system. So work done on the system actually is written as W is equals to P delta V, assuming that P is constant. Assuming P is constant. It may not be constant, okay, but assuming P is constant, this is the equation that you would get, which is something you have seen in, AS physics, right, in chapter 6. So work done on the system means the volume of the system is decreasing. So you're doing work on the system. You're sort of compressing the system. You can think of it like that. So if delta V is negative, then the work done on the system is positive. If delta V is positive, so your volume is increasing or the system is expanding, then the work done on the system would be negative. Okay, and another term that you have to know is something called the work done by the system. So if your volume is decreasing, that means the work done by the system is going to be negative. If your volume is increasing, then the work done by the system is positive, because the system, which is, you can think of it as some gas or some kind of matter that occupies some volume, is doing work on the atmosphere. So it's work is being done by the system, so it expands. Okay, essentially the signs are opposite for these two, so just something to be aware of. But for the first law of thermodynamics, if they write this equation here, by convention, this third term over here always refers to the work done on the system, which means we have to follow this convention. Okay, not work done by the system, it's always on the system. This is always supplied. So if they give you the first law of thermodynamics, and for this term they give you a negative number, that means work is being, well, that means you get a, if this is negative, that means the system is expanding. Okay, so there we go. Right, let's do some questions. So if you want to know how you get the first law of thermodynamics, there's a little explanation over here. This is not in the syllabus though, that's why I've put this bar over here. So if you're curious, you can have a look, but this is not important, so I'm not gonna go into detail here. I'll just leave it here if you are interested. Okay, so you can just write that down. Delta U equals to Q plus W. Okay. Let's do some questions on the first law of thermodynamics first before we do these questions here. So let's skip these and we're gonna jump to 4. On the figure below, place a tick against those changes where the internal energy of the body is increasing. Okay, so there are two ways of expressing the internal energy. One is by using the first law of thermodynamics, which is this guy here. The second one is by doing change in total kinetic energy plus a change in total potential energy. So if it's an ideal gas, you can probably use this one. If it's not an ideal gas, you have to choose one. Okay, so let's say water freezing at constant temperature. So if you see constant temperature, what that means is that the change in the kinetic energy of the particles in the substance is 0, because the temperature depends on the mean kinetic energy of a substance. Okay, so if the constant temperature is 0, constant temperature, that means this thing is 0. And water freezing means, let me think. So water freezing means the average separation between the particles. So if you're going from liquid to solid, normally the average separation would decrease, right? Because solids are denser. But water is a bit different because ice floats on liquid water. Ice is, solid water. So ice is actually less dense than water. So the average separation actually increases. So the change in EP should be positive. So if you use these two facts and then you put them into this second equation here, you see that the change in the internal energy would be increasing. What if we use this one instead? What if we use our first law of thermodynamics? Can we arrive at the same conclusion? Well, let's see. If water is freezing, that means Q is going to be negative, right? This guy is going to be negative because heat is being taken away from the substance. And W is going to be P delta V, but the thing is we don't know what the pressure is constant. So work done on the system, but it's expanding, so work is being done by the system, so this should be negative, but then you don't know whether the pressure is constant or not. So you can't really tell from the first equation whether it's positive or negative, but I think the answer should be increasing. So the internal energy should be increasing, if I'm not mistaken. Okay, the second one, you have a stone falling under gravity in a vacuum. So if you have a stone falling under gravity in a vacuum, okay, let's see. You would think that the gravitational potential energy is decreasing, right? If you drop something, the GPE decreases, but this potential energy term here in this equation does not actually refer to the potential energy of the substance of the system as a whole. It refers to the potential energies of the particles in the system. So the GPE doesn't actually play a role in the EP over here. Okay, so for this EP, you only look at the average separation of the particles. You don't care whether it's falling, whether the system is falling, or whether it's being, taken up. You don't care about that. So this falling here is inconsequential. We don't care about this. So a stone is falling under gravity in a vacuum. If it's in vacuum, that means there's no air resistance, because normally if you have air resistance, then you're going to get friction on the stone as it falls, and friction is going to cause the temperature to go up, which means your mean kinetic energy would go up, which means this term would be positive, right? But because it is in vacuum, there's no air resistance, therefore we can assume that the temperature is constant. So we know that delta EK must be constant, and this is a stone. It is not changing state, therefore the average separation between the molecules should remain the same. So this is 0, which means our change in internal energy would be 0 as well. So this is a constant, or delta U equals 0. Next up, we have a water evaporating at constant temperature. So constant temperature, again, means your change in this guy is 0. And your water is evaporating. So water evaporating means you're going from liquid to gas. Gas, the average separation is much further than liquid. So the change in EP should be positive as well. Therefore, this should be increasing. Okay. Part 4, stretching a wire at constant temperature. Again, same thing. This guy is 0. Stretching means you are increasing the average separation of the molecules, so therefore this guy should be greater than 0. Again, this should be increasing. There. Okay, so that's it. We haven't actually used this equation yet, so we'll get to that soon. I think it's one of the later questions. So for now, let's just double back and do question 1. You have a kettle rated at 2.3 kilowatts. You have a mass given at some temperature poured into the kettle. When you switch the kettle on, it takes 2 minutes for the water to start boiling, and a further 7 minutes, 1/2 of the water is boiled away. Okay, so in 7 minutes, 375 grams of the water is being boiled away. So that's the change in mass. Anyway, we're looking for the specific heat capacity. So we will have to use the equation delta Q equals to mc delta T. So C is this guy over m delta T. Delta Q, you can use the definition of power. Power is delta Q over T. So delta Q is equals to PT. So we can get PT over m delta T here. Oh, so P is going to be the power, which is 2,300 watts. The time taken is about 2 minutes for it to start boiling. So that would be 2 times 60. The mass of the water that you are boiling is 0.75 kilograms. And the change in temperature for it to boil is you're going from 20 degrees Celsius to boiling temperatures, which means it's 80, right? So using your calculator, you get 4,600 joules per kelvins per kilogram. And done. There we go. Next up, the specific latent heat of vaporization. So how do I find the specific latent heat of vaporization? Well, you just have to use the equation again. Delta Q equals to L delta M. So L is going to be delta Q over delta M. Delta Q is going to be PT over delta M. P is going to be 2,300. T again, T is the time taken for it to boil. So in a further 7 minutes, so it's 7 minutes, so that's 7 times 60. And then delta M is the change in the mass of the substance, or you can think of it as the amount of water that is boiled away in 7 minutes. So if you look at this, it says 1/2 the water is boiled away. So 750 grams divided by 2 is 0.375 grams. So putting that into the calculator, times 7 times 60 divided by 0.375, we get 1, 2, 3, 4, 5, 6. Wait a minute, that's a lot. Did I mess up? Hang on. That seems a bit unusual. Huh. Why is it so gigantic? Hmm. 1, 2, 3, 4, 5, 6 megajoules. What? Is that correct? That seems kind of weird. Hang on, let me just check. Oh, it is correct. Okay. So 2.58 times 10 to the power 6. There we go. So state one assumption made in your calculations and explain whether this will lead to an overestimation or an underestimation of the value for the specific latent heat. So what assumption do you think we have made here when we are doing these calculations? What do you guys think? What have we assumed here? No water vaporized during the 2 minutes of heating. True. Yeah, true. That is correct. So another assumption that we have also made is that there is no heat loss to the surroundings. Okay, so is this going to lead to an overestimation or an underestimation of the specific latent heat? What do you guys think? So if you were to account for this assumption, and then you compare it with this value here, is the actual value going to be higher and or lower than this? Is this value an overestimation or an underestimation of the actual value? So I give you guys some time to think, then I'll tell you the answer. Or maybe you could explain to me why you think it is an overestimation or underestimation. Okay, so let's say we go with 1007 suns, no water vaporized during the first 2 minutes of heating. So in fact, when you are heating this guy as it's boiling, the delta M would there's actually this constant rate of evaporation that happens regardless of whether it is boiling or not. So you think in 7 minutes 375 grams have evaporated, but in reality maybe only 350 grams has been boiled away due to you supplying excess heat to the system, and maybe 25 grams have evaporated because that's just the constant rate of evaporation, which means this value is actually a bit higher than the actual value. So this value should actually be a bit lower, which means your L should actually be a bit higher. Okay, which means whatever you get here is an underestimation of the actual value because the actual value is a bit higher. Now, if you were to go with the other assumption, so the other assumption is no heat loss to the surroundings. So you think you've put in, let's say, you've put in 10,000 joules into the system during that duration of time. You've put in 10,000 joules, and you assume that all 10,000 joules gets absorbed by the water. But in reality, what's actually happening is maybe only 9,000 joules get absorbed, and 1,000 joules gets lost to the surroundings. So you think you've put in, 10,000 here, but what's actually happening is you're only putting 9,000. So the actual value, this guy is going to be a bit lesser, which means this guy here, the actual value would be a bit smaller. Hang on, that contradicts each other. That's kind of weird. Let me think. They shouldn't contradict each other because they should give you the same thing. Let's see what the answer is. Assumption no heat loss, power constant. I didn't include the explanation. Let me think again. Hmm. Hmm. Oh wait, I don't think you actually include the constant rate of evaporation when you're boiling something. So when you're boiling something and it's changing from liquid to gas, it is also accounting for the evaporation rate as well. So you don't have to treat them as separate things. So this is actually already accounting for that. So if you're going with that and saying that during the first 2 minutes there's no water vaporized, would that affect any of these calculations here? Let me think. I don't think it would, because the difference would still be the same, right? Because we are only interested in the difference. We're not interested in the where it originally started. So since we're only calculating the difference, I don't think it really makes much of a difference if you assume whether the water vaporized during the first 2 minutes or not. Yeah. So I think the only assumption that you can make is saying that there's no heat loss to the surroundings, and that would affect this L here. So the actual value, so you imagine you put in 10,000, but only 9,000 goes in. 10,000 is lost, which means the actual value should be lower. So this guy should be lower, which means L is lower. So whatever we get here is actually an overestimation. Yeah. So this is an overestimation because the assumption is no heat is lost to the surroundings. Okay, so there we go. Okay, moving on. So now you have a mass of ice at some negative 15 degrees Celsius taken from a freezer placed in a beaker containing 200 grams of water at 28 degrees Celsius. Data for the ice and for water are given below. Calculate the quantity of thermal energy required to convert the ice at negative 15 to water at 0. So the way I like to solve questions like this is by drawing a little flow chart. So you start with ice at negative 15, so you can draw like a line. Okay, so this is ice at negative 15 degrees Celsius, and you want to change that to water, right? So in order to change the water, you have to increase the temperature of ice until it reaches 0 degrees Celsius. But it's still ice. And now you have to change the state of ice to water. 0 degrees Celsius. Remember, when you change states, the temperature doesn't change. So you have two stages and you have to add up these energies here. So E1 here, E2 here. So the total energy required is E1 plus E2. So E1 is going to be equals to mc delta T, because you are just changing the temperature, we're not changing the state. E2 is going to be L times delta M. So the first one is M is 24 grams, so 0.024. Okay. And then C is the specific heat capacity of ice, which is 2.1 times 10 to the power 3, and the change in temperature is 15, positive 15. So just put that in, and we get 756 joules. Okay, what about this one here? So this one is 3.3 times 10 to the power 5 times 0.024. Which gives 7,920. Okay. So the total is just going to be this plus that, which is 8,676 joules. There we go. By the way, as you probably are aware, the school usually has like a parent-teacher meeting thing at the end of a term, right? But for A levels, we are not having it officially this term. However, if your parents would like to get in touch with the subject teachers, you can just reach out to us and let us know, and then we will schedule an appointment. Most likely next week or the week after next. Okay, so even though it's not there, it's not official, but we are more than happy to accommodate if you guys have any concerns that you want to talk to us about. So feel free to let your parents or guardians know about this. Okay, anyway, or if they just want to have a chat, sure, why not? Okay, anyway, we're gonna continue. Assuming that the beaker has negligible mass, calculate the final temperature of the water in the beaker. Okay, so this one is a bit tricky because if you look at the question, it says you're putting some ice in some water, which means they are going to mix, right? Now, the thing about this is when you put two bodies of different temperatures next to each other, what's going to happen? The bodies are going to reach thermal equilibrium, which means the hotter body would cool down, the cooler body would warm up, and eventually they would reach the same temperature, okay? And then that's when it stops. And the rate at which it cools down or warms up depends on the difference in the temperature. But that is not in the syllabus. But if you eventually study about that, it involves a differential equation. Anyway, we'll come back to this. Okay, so how do I do this question? Well, again, you want to draw the flowchart. So let me show you how to do that. Maybe I should do it here. Okay, let me do that here. Zoom this in a little. So you have water at 28 degrees Celsius. Okay, and how much water do you have? You have 200 grams of water. And then what's going to happen here is you're going to drop the temperature of this water to some new temperature, which we do not know. So I'm going to call that K degrees Celsius. And this is going to be the mixture. So water at 224 grams. Okay. And then you have your ice cubes, which you have put down here. Your ice cube is over here. Ice, 24 grams. It starts at negative 15 degrees Celsius, and then it's going to go up to ice again at 24 grams. But this is now 0 degrees Celsius, and then it's going to change state. So this is now water, 24 grams, 0 degrees Celsius. And then it's going to increase its temperature to this guy right here. And that's when they sort of merge together. Okay? So we actually know what this is. This is actually going to be positive 8676. What we got earlier. So this is 8676 joules. Okay. And then we also have this guy here, which we'll call E1. And this guy here, which we'll call E2. So, by the conservation of energy, we know that the change in total energy of a system must be 0. So what it tells you is that the gain in energy of a system must be equal to the loss in energy of a system. So the gain is going to be E1 plus 8676, and the loss is going to be E2. Okay, so E1 is going to be, what is E1 going to be? MC delta T. So M is 0.024. 0.024. C is, what is C for water? Water is 4.2. 4.2 times 10 to the power 3. MC theta. Theta is from 0 degrees to K degrees, so it increases by K, plus 8676. And then E2 is going to be the loss. So the loss itself is defined as a positive number, okay? So we don't have to put a negative here. So M is going to be 0.2 times 4.2 times 10 to the power 3. And then you start at 28 degrees and then go down to K. So that's going to give me 28 minus K. Okay, so now we can simplify this using a calculator. What do we get? We get 100.8 kelvins. No, not kelvins, what I'm saying. This is a constant K, not kelvins. 8676 equals to 0.2 times 4.2 times 10 to the power 3 times 28, which is 23520, minus 0.2 times 4.2 times 10 to the power 3, 840K. So we get 940.8K here. Then 23520 minus 8676, which is 14844. So K has got to be 15.78 degrees Celsius. So that is how you work out the final temperature of a mixture of two different things. With some ice and some water, the ice melts. What's your final temperature of water going to be? 15.78 in this case. Okay, so there we go. Done. Is this okay? Anything you guys wanna ask? So the first thing you have to do is always draw the flowchart, so you know exactly what to do later. So draw the flowchart and then use conservation of energy. Say gain of energy equals to loss in energy, put in the values, and then you work it out. That's it. Okay, right, moving on. Let's look at question 3. The volume occupied by 1 mole of liquid water at 100 Celsius is this guy. When the water is vaporized at the atmospheric pressure of this guy, the water vapor has a volume of this. The latent heat required to vaporize 1 mole of water at this temperature is this guy and this guy. Determine for this change of state the work done on the system. So you can see that the water is being vaporized at a constant pressure. Constant pressure means we can use W equals to P delta V. Oh, whoops, I messed up my W. P delta V. So what is P? P is gonna be, what's P? P is 1.03 times 10 to the power of 5. So this is work done on the system, all right? And you can see that the water is being vaporized, which means your volume would increase. So the work done on the system should be negative, because if the work done is positive on the system, then it should be decreasing the volume, right? So we're gonna put here as negative. What is the change in volume? Change in volume is, okay, you can see this, the final volume is 2.96, initial volume is 1.87. So you're essentially taking 2.96 times 10 to the power minus 2 minus 1.87 times 10 to the power minus 5. That's the change in volume. Okay. And we go. Here we go. 2.96 times 10 to the power negative 2 minus 1.87 times 10 to the power negative 5. Get a negative number for that, times 1.03 times 10 to the power 5. We get negative 3047 joules. So when it comes to work done or work done on the system or work done by the system, the signs are very important. Usually they would allocate 1 mark for the sign. So make sure you put in the correct sign. In this case, it should be negative. So next up, we're going to find the heating of the system. Right, so the heating of the system, if you use the first law of thermodynamics, refers to the Q. Okay, so you're trying to find Q. So Q is going to be delta U minus W. So what is delta U here? Do we know what delta U is? We don't. The heating of the system. Oh, wait, hang on. The latent heat required to vaporize 1 mole of water at 100 degrees Celsius is this. Is actually given. So we have 1 mole of liquid. There's 1 mole. Okay, so this is actually the answer. It's actually given to us indirectly. So it's 4.05 times 10 to the power 4. You don't even have to use this to calculate. So this is 4.05 times 10 to the power 4. Now we have to find the increase in internal energy of the system. So now we have to find delta U. So to find delta U, you have to use the first law of thermodynamics, which is Q plus W. Q is going to be positive because you are supplying heat into the system. So 4.05 times 10 to the power 4. W is going to be negative because work is, not being done by the system. Work is being done by the system, so it's expanding. So this one should be negative, whatever we got earlier, which was 3047. Okay, now I'm going to put that into the calculator. And you get 3.75 times 10 to the power of 4 joules. And done. Okay. Using your answer in A part 3, estimate the binding energy per molecule in liquid water. So, how do I explain this? Let me think. Okay, so whatever change or whatever increase in internal energy of a substance when you change the state of a substance is the increase of internal energy is going to be distributed to the molecules in the liquid water. Okay, so what you got to do is you have to take the increase in internal energy and divide that by the number of molecules. In this case, you have 1 mole. So it's 6.02 times 10 to the power 23. So that's how you find the binding energy per molecule. So divide that by 6.02 times 10 to the power 23. And then you get 6.23 times 10 to the power negative 20 joules per molecule. There. Okay. We're done with this, and then we have this guy here. Right, so this one is actually a pretty tricky question. You have a jeweler. I think this is probably the hardest question for this chapter. You have a jeweler wishing to harden a sample of pure gold by mixing it with some silver so that the mixture contains 5% of silver by weight. So the final mixture would be 5% silver. The jeweler melts some pure gold and then adds the correct weight of silver. The initial temperature of the silver is 27 degrees Celsius. Use the data from the figure below to calculate the initial temperature of the pure gold so that the final mixture is at the melting point of pure gold. Okay, so you have two things. You have gold, you have silver. You're trying to mix them together so you get some kind of alloy, which is 5% silver. So what is the initial temperature of pure gold? Okay, right. In order to mix metals together, they must both be in liquid form, right? So since your silver starts off at 27 degrees Celsius, you have to heat up your silver first to melt it. So let's draw a flow chart. So let me see if we can draw it over here. You have your silver at 27 degrees Celsius, silver, and then we're gonna call this 0.05 M. So M is the mass of the final mixture, and we want silver to only be 5% of the final mixture's mass, because mass is proportional to weight. So that's why we are calling it 0.05 M here. Okay, and then the initial temperature is 27 degrees Celsius. So we're gonna have to increase the temperature of silver until it reaches the melting point. So silver 0.05 M. What is the melting point? Melting point of silver is 1240 kelvins. So you know what? I'm going to change my 27 degrees Celsius to kelvins, which I'm going to add 273 to that, which gives me 300 kelvins. Okay, so now this is a solid silver, and now we're going to melt it. So when we melt it, we have to use another row, because, you know, we have to use a different equation since you are melting it at constant temperature. Okay, and now that it is finally melted, we want to increase this again so that the final mixture's temperature is at the melting point of pure gold. See, the final mixture is at the melting point of pure gold. So therefore, we have to increase this to 1340 K. So this is going to be silver and gold, and then this is in liquid form, and then M is some constant M here. There we go. So now we have our initial temperature of gold, which we don't know. So gold is going to be, it's going to have to be a liquid gold, because it has to be hotter than silver, so that when you mix them together, gold would decrease and then silver would increase. So the initial temperature of gold is going to be, we don't know what that is, so we'll call that T kelvins. All right. And then it has a mass of 0.95 M, 95% of the final mixture. And then we're going to have to decrease this to 1340 kelvins. Okay, that's it. So we're done. So we're gonna call this E1. We call this E2, E3, and E4. So what we have to do here is we have to say that the gain in energy is equals to the loss in energy. So we have E2 plus E3 plus E4 equals to E1. So let's work out each of them separately. So E2 is going to be from liquid silver to some hotter liquid silver. So what is the mass of liquid silver? That's 0.05 M. And then C, the specific heat capacity of silver is 235. Okay. And what else? Note that this is kilojoules. This is joules, so you have to change this to joules when you use the specific latent heat diffusion. Anyway, coming back to E2, MC theta. Theta is 100 kelvins because you're going from 1240 to 1340. So putting that into the calculator, we get 1175 M. All right, cool. Let's work out E3 now. E3 is the change in state of the silver. You're going from liquid silver. No, you're going from solid silver to liquid silver. So you have to use ml. M is going to be 0.05 M again. L is going to be the specific latent heat of fusion for silver, which is 105 times 1000 because it's in kilojoules. Okay, 0.05 times 105,000 gives us 5250 M. And then for E4, what do we have? E4 is going from solid silver to the melting point of solid silver. So again, it's 0.05 M. Specific heat capacity of solid silver is 235. And then times another 1240 minus 300. That's 940. 940, which is 0.05 times 235 times 940. 11045. So in this case, it's a little special because the specific heat capacity for liquid and solid silver are the same. So we can just use 235. But usually for most substances, I think they are slightly different. Anyway, now that we have worked out all these values here, I forgot an M here, we can work out E1. Wait a minute. Yeah, we can work out E1. So what is E1 going to be? E1 is going to be MC theta. So M is 0.95 M. C is 129. Theta is going to be T minus 1340. There we go. Okay, so E2 plus E3 plus E4. What do we get? 1175 plus 5250 plus 11045. That's going to be 17470 M equals to E1, which is 0.95 times 129. We get 122.55 M minus 0.95 times 129 times 1340, which is 164217 T. No, there's no T. There's a T here. There's an M here. Okay, there we go. So now we can get rid of all the M's. And then we can work out what T is. So 17470 plus 164217 divided by 122.55. That's going to give us 1483 kelvins. So the initial temperature of gold has to be 1483 kelvins. There we go. And done. So, is that okay? You guys good? Okay. Suggest a suitable thermometer for the measurement of the initial temperature of the gold. Okay, so which thermometer do you think you should use to measure 1483 kelvins? What do you guys think? What's a suitable thermometer? So from the last chapter, we did 3 different thermometers, right? We did the mercury and glass thermometer, the one that you see in your chemistry labs. We have the thermocouple, and we have the thermistor. So among these 3, which one do you think we should use to measure 1483 kelvins? The thermocouple, yes, correct. That is right. The thermocouple is the one you want to use for measuring extremely high temperatures. You can't use the mercury in glass thermometer or the thermistor because they're just gonna melt. Okay. Besides, the thermistor is only good for measuring a small. Okay. The reason you use a thermistor is to measure a small range of temperatures because thermistors are extremely sensitive. Okay. And yeah. Anyway, that's that. Okay, so we still have this guy here. 1, 2, 3, 4, 5, 6. Still have 6 questions to go. Hum, 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 hum. Let me think. Do we want to go through this one? Yeah, okay. Let's do one more. Let's do one more. So you have a mercury in glass thermometer. Okay, you're measuring this temperature of this oil. The oil has some mass 32, specific heat capacity, and the actual temperature of the oil is 54. The bulb of the thermometer has, okay, so the bulb here refers to the little thing at the bottom of the thermometer. Has a mass of 12 grams, average specific capacity of this. Before immersing the bulb in the oil, the thermometer reads 19 degrees Celsius. The thermometer bulb is placed in the oil and the steady reading on the thermometer is taken. Okay, so determine the steady temperature recorded on the thermometer. Right, so this one again is like a mixture kind of question. So when you actually take the thermometer and you put it into a substance and then you measure the temperature of the substance, you're not actually measuring the actual temperature of the substance because when you put your thermometer in a substance, some heat is going to be absorbed by the thermometer, which means your actual temperature of the substance is going to drop by a tiny amount. So you're actually measuring the final temperature after the thermometer has achieved thermal equilibrium with the substance, not the actual temperature of the substance when you measured it. Okay, so you have an oil which is 54 degrees Celsius, and then you have your thermometer bulb, 19 degrees Celsius, and it's going to increase the temperature here to some common temperature. Okay, so what is your final temperature? E1 is going to be mc theta. M is 32 grams. C is 1.4. T is, let's say this is T degrees Celsius. 54 minus T. E2 is going to be 12 grams. 0.180. And then T minus 19. Okay. So another reason why we use mercury in a thermometer is because mercury has a very small specific heat capacity, which means you only need to introduce a tiny amount of heat for the temperature to rise, which means you don't have to absorb a lot of heat to achieve thermal equilibrium, which means your reading would be more accurate to the actual, would be closer to the actual reading. So a good thermometer has a very small heat capacity, right? An ideal thermometer would have almost zero heat capacity. Okay, so let's work this out. We get 2.4192 minus 0.0448 T 2.16 times 10 to the power minus 3t minus 0.04104. Okay, so T is going to be equals to this guy, 2.46024 divided by 0.04696, which is 52.4 degrees Celsius. Say, there we go. So you're trying to measure, and you know that the actual temperature is 54 degrees Celsius, but when you've actually measured it, the temperature is 52.4 on the thermometer. So if you really want to work out the actual temperature, you have to get the measurement, which is, let's say, 52.4, and then you have to plug it into this equation to work out the actual temperature before you took the measurement, because the act of measurement changes the results. Kind of like quantum physics, actually. Okay, so next up, we have the ratio of the change in temperature to the initial temperature. So the change in temperature is 54 minus 52.4. The initial temperature is, of course, 54. So 54 minus that divided by 54 gives me 0.0298, which is roughly 3% difference in the actual temperature. So just an explanation, a type of thermometer that would likely to give a smaller value for the ratio calculated in A2, this guy. So what kind of thermometer would give a smaller ratio? As I've mentioned earlier, a thermistor is very good because it's, very good for measuring small ranges in temperature because it is very sensitive. And the reason it's very sensitive is because the specific heat capacity is very small. So you want to use a thermistor because the C, the specific heat capacity, is smaller. There. Okay, so that's it. The mercury in glass thermometer is used to measure the boiling point of a liquid. Suggests why the measured value of the boiling point will not be affected by the thermal energy absorbed by the thermometer bulb. So, why is it that when you measure the boiling point of a liquid, it would show 100 degrees Celsius on your thermometer, even though, you know, this phenomenon is happening? So some energy is being absorbed by the thermometer, right? So why is the thermometer not showing something different than 100 degrees Celsius? Why do you think that is? So the way you sort of make sense of this is, let's say I boil the water, right? And then it goes from 90, 95, it's not boiling yet. And then when it goes to 100 and it starts to boil, and then you put in your thermometer. So what happens when you put in your thermometer? The temperature is going to drop to maybe 98.4. Hey, Carrot, hello. So when the temperature drops to 98.4, it's going to stop boiling because it's not at boiling temperature. So your thermometer will read 98.4, and then you would interpret it as, oh, it's not boiling yet. So now you're going to put in more heat, which means it's going to go up to 100 degrees Celsius, and whatever surplus energy is going to get sent to your thermometer bulb, which means no matter what happens, you're going to read 100 degrees Celsius on your thermometer bulb. So the way you want to sort of write this is by saying the temperature of the boiling point is constant, so the heating of bulb would only affect the rate of boiling. So it would slow down how fast it takes to boil something, but it's going to boil at the same temperature regardless, if that makes sense. Okay. And that's it. Okie dokie. Right, so we still have 1, 2, 3, 4, 5. We have 5 questions to go. I think we'll save this for our next class, which would normally be this Friday, but unfortunately we have the graduation of your seniors going on. So I'll be busy this Friday, which means we'll have to cancel the class for Friday, and I'll see you guys next week. Yep. So my last class with you guys would be on the 17th of July, I think. No, wait. 16th of July. Yeah, 17 is a Saturday. So my last class with you guys will be on the 16th, which means next week would be our last class. And next term, I believe a new teacher is taking over, and I think his name is Mr. Zikri. So yep, I will let him know where we've stopped, and then he will take over next term in September. So we'll stop here for today, and I'll see you guys later for math. Alrighty, bye bye.